very pleased to have Hao Zhang from Tsinghua University, who will tell us about sewing and factorization of smooth and nodal conformal blocks in logarithmic CFT.
I'd like to thank Professor Ranko for introduction, and I'd like to thank the organizer for giving me this opportunity to give this short talk. And the title of my talk today, as you can see, is called the sewing and factorization of smooth and nodal conformal block functors. So the final goal of my talk is to give the following picture. Only one side, we would like to consider something called smooth conformal block. And on the other side, we would like to consider nodal conformal block. So in my talk, the main goal is to compare these two things. And so what happened? So
maybe if you have to unfull screen once.
Okay.
Now it switches the slide. Now it works.
Okay. So the talk is based on the following 4 papers. The first 3 papers is a joint work with Bing Gui. The final goal of the first 3 papers is to give some formulations of the so-called sewing and factorization theorem in logarithmic CFT. And in Professor Gui's talk, he has already introduced some of the applications of one forms of the sewing and factorization theorem, as you can see. In this talk, I will give another formulation of this SF theorem. On the other hand, I would like to introduce the non-equivalence of the smooth and nodal conformal block functors. This result is based on the last paper here. Since we are considering logarithmic CFT, I will fix a C2-cofinite ungraded VOA V, which is not necessarily self-dual or rational, which means I will consider, for example, the triplet W algebra, the even symplectic fermion VOA, or the WPQ algebra throughout my talk. The representation category of V is denoted by mod V. Mod V is the category of grading restricted generalized V modules. By Huang Lepowski Zhang, this category is a braided tensor category. Let me start with the smooth conformal block functors. Let X be an unpointed compact Riemann surface with local coordinates. Here, the underlying Riemann surface of X is C. C has n distinct map points x1 to xn. Each map point xi is equipped with a local coordinate eta I. The smooth conformal block functor associated to X is a left-z contravariant functor CBX from mod V tensor n to vect. The vect is a category of finite dimensional C linear category. The finite dimensional C vector spaces. The functor is defined as follows. First, you pick a V tensor n module W here. Then you assign this W to the ordered marked point x1 to xn, which means you have to associate each V action yi to one of the marked points. You have fixed such an ordering. Then CBXW consists of linear functional W to C, which are invariant under certain intertraining properties. So it is useful to consider the graphical calculus in the theory of conformal blocks, just as the theory in the topological quantum field theory. In our picture, the picture for CBXW, the space of conformal blocks, is the following picture. You can see that here we have a genus 2 5-pointed Riemann surface with local coordinate. And we have a V tensor phi module. We assign the V tensor phi module W to the marked point. Then this this formula represents the space of conformal block CBXW. If you want to reverse the arrow, you have to simultaneously replace your module by its contributing module, which is denoted by W prime. And in practice, it is often useful to divide our set of marked points into several subsets. For example, in this picture, we divide our marked point into red point and blue points. In this picture, we have 3 blue points and 2 red points. We associate a V-tensor 3 module X to the blue point, as you can see here, and another V-tensor 2 module Y prime to the red point here. Then, by just as what I said, we can reverse the arrow and simultaneously replace the module by its contributing module. We can these 2 space of conformal blocks are equal. More precisely, any conformal block in this space can be viewed as a linear map from X to the algebraic completion of Y, satisfying certain intertraining properties. Okay, if you want to consider higher genus conformal blocks, it is necessary to consider a procedure called sewing conformal blocks, or in particular, composing conformal blocks. Here, we first have 2 conformal blocks. The first is phi here, another is psi here. Then, geometrically, the phi is a conformal block of this type, and psi is a conformal block of this type. Geometrically, we can solve pointed Riemann surface along certain local coordinates. We use the local coordinates of the blue points to geometrically solve the Riemann surface. You have to use the local coordinate to cut off some unit disk and glue some of the remaining part, and then you will get a higher genus Riemann surface with marked points. Algebraically, we can define a sewing or composing conformal block by the following formula. In this formula, P lambda bullet is a projection map from the algebraic completion of Y to the generalized eigenspace of L0 with eigenvalue lambda bullet. So each term is well defined, but this is an infinite sum. So we have to prove some convergence problem in order to get the higher genus conformal block. And this problem is solved in our second paper with Binggui. And we prove that this infinite sum is actually well-defined and converges to a conformal block of the higher genus Riemann surface. So we can consider, we can compose or solve conformal blocks to get a higher genus Riemann surface.
Excuse me.
Okay.
Is P lambda bullet an intertwiner for the vertex operator action or not?
It is a projection map, like it's like.
Does it commute with the action of the vertex algebra?
Yeah. Of course, it is a polynomial of L0, some kind of thing like that. So you can it is not necessary that you can. Eventually, it will be something like lambda bullet, and the lambda bullet is like this. Then this is some kind of projection, and this projection you can prove that in the finite dimensional filter space, it is a polynomial of L0. It's something like that, but it is quite complicated to prove the convergence of this infinite series.
each individual p lambda dot, each individual projector does not commute with the
Yeah. It not necessarily commute with the phi or cosine or something like that.
It does not commute.
Not commute.
Yeah. It does not. Of course, it does not commute. Okay, so this is a convergence of Sawing conformal blocks.
The point is when I put the superscript, now I'm kind of thinking about mapping to some completed space, and so I'm.
So you can view this kind of thing exactly the same thing as the formula inside the bracket. It's just the different expression of the same conformal block. So if you define this something like the subscript, then you can define something under the subscript. Okay, this is our homogeneous conformal block. So we can give the formulation, another formulation of Sawing factorization theorem using the Sawing conformal block. Since we have already proved the convergence property, we then obtain the Sy, which is given by Sawing or composing conformal block. This is a denatural transformation. It is easy to check that it is a denatural transformation. And as y varies, Sy gives is exactly a coend, which means that the coend of the tensor product of the space of conformal blocks is equivalent to the space of conformal block of homogeneous. And this version of Sawing and factorization theorem is given by Zhang. This amounts to say one particular application of this theorem is the associativity of the genus zero theory. In the genus zero theory, this is mainly due to Zhang. And in a more general setting, this is due to Moriwaki. Okay, this is another formulation of the Sawing factorization theorem involving the coend. In practice, it is often useful to give a formulation of Sawing factorization theorem involving the fusion product and the canonical conformal block. So we fix a V tensor n module X and consider the geometric data X here. Here X is a compact Riemann surface with n incoming points and k outgoing points. Here the incoming points is the blue points, and outgoing points are the red points. If you fix X, and then this space of conformal block will give a left exact functor from the mod V tensor K to the finite dimensional C vector space category. Since every left exact linear functor from a finite C linear category to the vector space category is representable, there is a Y natural isomorphism like that. This isomorphism means that we have a V tensor K module here that represents the conformal block functor. And this V tensor K module is unique up to an isomorphism, and we call this V tensor K module the fusion product.
So if you're using the existence of projectives?
Which is projective?
So do you use the existence of project? I mean, like if you have some left exact functor representability, I mean, don't you need like some, that there exists finally some finiteness properties on the category?
Yeah, because this theorem is based on a finite C linear category. You have to use some finiteness. Because our V is C2-cofinite, the mod V tensor K is a finite C linear category. Okay, so in this isomorphism, we can choose Y to be the fusion X itself. Then the home space becomes an endomorphism space. Then the identity map in this endomorphism space corresponds to a conformal block on the right-hand side. And this conformal block is called the canonical conformal block. So to summarize, our fusion product is something that represents the smooth conformal block. So the fusion product is something on this side, on the left-hand side, not on the right-hand side. Okay, we are now ready to give the next formulation of our Sawing and factorization theorem involving the fusion product. Recall that we have the canonical conformal block here. Then by composing the canonical conformal block, we have an isomorphism from the lower genus conformal block space to the higher genus conformal block space. Because for each conformal block cosi here, then we can compose a conformal block of this type, then you will get this conformal block, a conformal block of this type. And this linear map is not only a linear map, this is an isomorphism. And this isomorphism is called the Sawing and factorization isomorphism. It is really easy to memorize this theorem because you only need to consider the higher genus conformal block space and remove and replace the red part by its fusion product. Then you will get the conformal block you can get the lower genus conformal block space. And the isomorphism is built by the canonical conformal block and the sawing conformal block. So this is really easy to memorize. So our solution to the smooth conformal block is the sawing and factorization theorem. And this corresponds to an object that is called the fusion product. So this is our solution for the left-hand side. It is really easy to prove the sawing and factorization theorem B from the sawing and factorization theorem A. First, you need to write the higher genus conformal block as the coend of the tensor product of two spaces of lower genus conformal block. Then, by the definition of fusion product, you can write this space of conformal block as a home space. And since the coend of the home functor and another functor is equal to their composition, so then we will get the conformal block on the here. And the last step uses the isomorphism due to Lubashenko and Fuchs and Schweiger. So it is not hard to in fact, we can use this formula, this method to prove that the A and B are actually equivalent. But in this slide, I will only present one side. But there is application that can make you even more clear about what our theorem talks about. To begin with, we have to give an example of our fusion product. Our example is like the fusion product along this geometric data. This is a sphere with 0 input and 2 output. And you associate the C. C is considered as a mod V tensor 0. And you insert this C to the 0 punctures, and the fusion product coming out of the 2 punctures as a V tensor 2 module is the end. This has already been discussed by Professor Gui's talk, and let omega be the canonical conformal block of this type associated to the end or the fusion product. Then a special case of our sawing and factorization theorem gives a sawing and factorization theorem really similar to the picture that is called the self-sawing. So the linear map by composing the canonical conformal block omega will give an isomorphism from this space of conformal block to this space of conformal block. So to summarize, what we get is that factorization of smooth conformal block is given by the object and which is a V-tensor 2 module. By replace the cap here by a V-tensor 2 module called the end. In the C2-cofinite and rational case, this theorem is given by Damiolini, Gibney, and Tarasca. In that case, it can be written as a direct sum over simple modules of x and x tensor x prime. So this can be viewed as an alternative of their result in the logarithmic case. So maybe we can write the object and here, because and is a special case of the fusion product. The and is more precisely, this is the and E. Okay. Sorry. Yeah. So we are let us turn to the second part of my talk. We want to review some history in the rational CFT about the factorization of conformal blocks. This history is mainly about algebraic geometers. So we assume that V is ungraded C2-cofinite and rational in the following 2 pages, where we talk about the rational CFT. And for the Virasoro VOA and the higher genus case, this topic is discussed by Bellingson, Fingen, and Mazur. And for the affine algebra or the affine VOA, for the higher genus case, this is mainly due to Tsuchiya, Yuno, Yamada, Bakalov-Pirov, and Ui-Yanga. And for the genus 0 case, for the general VOA, in general VOA, I mean the VOA of satisfying the condition like that. This is due to Dactomo and Tsuchiya. And for the general VOA and the higher genus case, this is finally solved by a remarkable result by Damiolini, Gibney, and Tarasca in 2019. And in my talk, I will use the setting of Damiolini, Gibney, and Tarasca to give an introduction. To summarize, their approach involves the following 4 steps. First, now we only give the definition of conformal block for smooth curves. First thing we need to do is to generalize the space of conformal block to the nodal curves. We have to take into consideration the nodal curves. Then we have to prove a factorization of nodal curves. And the solution in rational CFT of this thing is given by the irreducible V modules. They give an isomorphism like this. And by the infinitesimal smoothing of the above isomorphism, more precisely, they consider the smoothing of nodal curves. The above nodal factorization will give the fact that the space of conformal block will form a vector bundle on the MGN bar on the moduli space. Then we will have the factorization of smooth conformal block, which is just this isomorphism by replace the nodal curves by the smooth curve. So the smoothing is important in their argument. So let me summarize their method. The method they use for nodal curve is called the nodal factorization. And in the rational CFT case, the object is given by the irreducible modules. But in the logarithmic case, it is given by the so-called mode transition algebras, as I will introduce soon. Now we return to our discussion about the logarithmic CFT. So we return to the assumption of that V is ungraded and C2-cofinite. The mode transition algebra A was introduced by Damiolini, Gibney, and Tarasca in 2022. This is defined first as an object in a mod V tensor 2, then as an associative algebra. As an object in mod V tensor 2, A is defined by the two-sided induction of the level 0 Drude algebra. Then Damiolini, Gibney, and Krashen gives the nodal factorization involving the V tensor 2 module called the mode transition algebra. They give the nodal factorization here. So to summarize, the factorization of nodal conformal block is given by the mode transition algebra A. So the correct object here of nodal factorization is called the mode transition algebra.
Does this require rigidity, or is this without rigidity?
This does not need the rigidity. So throughout my talk, I will never assume rigidity. Okay, so this is a theorem of Damiolini, Gibney, and Krashen.
So is it that they prove that you're kind of a sheet, like a locally free sheaf with a flat connection on the MG bar? Therefore, in the boundary, there's some lower genus stuff, and then in the interior, you're higher genus. So I can kind of connect this. And is that kind of how you could think about this geometrically? Is moving from the boundary into the interior?
Yeah, it's something like that in the rational case.
Not locally free on the boundary, just in the interior. The locally free is only in the interior, but not in the near the boundary of the moduli space.
Yeah. In the rational case, it can be done in the whole compactified moduli space. But in the logarithmic case, we can do this in the interior of the moduli space, not cannot extend to the boundary of the moduli space.
This is the smooth versus nodal.
Yeah, smooth and nodal. Yeah. So I will present this result in the next page. So by the theorem of Damiolini, Gibney, and Krashen, the factorization of genus 0 conformal block can be applied in the nodal sphere here. This space of conformal block is isomorphic to the genus 0 smooth conformal block here by replacing this cup with the mode transition algebra. Then this conformal block space is identified with this home space involving the mode transition algebra. On the other hand, we can consider the genus 0 smooth conformal block, because the genus 0 smooth conformal block is rather easy in this case, because it is identified with a home space easily. Then by a theorem of Fuchs, Skolman, and Schweiger in 2016, we can identify this home space with this home space involving the end. So you can see that it is really natural to ask if the mode transition algebra is isomorphic to the NE. Because if it is isomorphic, then if they are isomorphic, then these must have the same dimension. But unfortunately, it is not always the case. In the rest of my talk, I will pick a C2-cofinite ungraded VOA that admits a module that is not generated by its lowest weight subspace. Many examples satisfying this condition, this additional condition, because, for example, the triplet algebra satisfying this condition. The even symplectic fermion VOA also satisfying this condition. And for this type of VOA, there exists some module X and Y such that the dimension of this two-pointed genus 0 smooth conformal block has and the space of genus 0 two-pointed nodal conformal block has non-equal dimension. We can prove this thing under the more general assumption of the the VOA like that. Then a simple application of this theorem is that by propagation of conformal blocks, the space of conformal blocks associated to this module will not form a vector bundle over the M0 n bar moduli space for any n greater or equal than 4. So this is not the same case as the rational CFT. Let me give a more precise choice of the X and Y. In our theorem before, we choose X to be an indecomposable projective module that is not generated by its lowest weight subspace, and Y to be an irreducible module or an indecomposable projective module. For example, in the triplet algebra case, X can be chosen to be the projective cover of this module X1 minus. This module is the unique irreducible module with maximal conformal weight. And the projective cover of this module is not lowest generated. So we can choose X to be this module, then the dimension is non-equal. Okay, we can get even more from our main theorem. What time is it? Okay. Recall that we already have the following characterization of nodal conformal blocks and a smooth conformal block. The nodal conformal block is given by the mode transition algebra A as a V-tensor 2 module. Another formulation, the characterization of smooth conformal block genus 0 is given by the end E. And since these two spaces has non-equal dimension, we can conclude that the end E is not isomorphic to the mode transition algebra A as an object in V-tensor in the mode V-tensor 2 category. And this answers a question of a recent paper by Damiolini and Voigt. And they ask under what conditions is these two objects isomorphic to each other. So our conclusion is that for VOA of our type, the two objects cannot be isomorphic to each other. Okay, that's all for my talk. Thank you.
Thank you. Are there questions?
Yeah, so you said this dimension issue comes up in the case of projectives. Does it also come up when you look at simple?
Because any simple module is generated by its lowest weight subspace. So if you consider only simple module, we cannot get the non-equality of the.
So there will be. Yeah. Okay.
I haven't think about this, but I think the main problem is the indecomposable projective modules. Because our proof relies heavily on the existence of the non-lowest generated modules, and we can prove that if there is a lowest generated module in the mod V, then there exists a simple module whose projective cover is not lowest generated.
And so which dimension is bigger than the other? In the
maybe from my proof I cannot see. Cannot see.
More questions?
So just algebraically, from the Damiolini and Gibney and Krashen viewpoint, they say that this smoothing can't occur. The smoothing has to be able to occur if I have these strong identities, a family of strong identities in my mode transition algebra. Can you tell me how so here you don't have such identities? How do I see?
There is no strong identity condition in my talk.
And can you tell me how I see this in this setting, the lack of these strong identities?
Yeah. Strongly identity condition is something that ensures that the dimension is equal. And since our dimension is not equal, so I think this implies that the VOA in my talk does not satisfy the strongly unital condition, a strongly identity condition.
But there's no direct way of seeing that. It's just you're using their theorem.
Sorry?
There's no direct way of seeing that. You're just using their theorem.
Yeah. So actually, we only use the structure of V tensor 2 module of their theorem. And in fact, in my proof, I don't use their mode transition algebra because I only need to use use some V tensor 2. We prove that there exists a V tensor 2 module that gives them this isomorphism. And we prove that this V tensor 2 module is lowest generated as a left V module. And since the V tensor 2 module that represents the nodal conformal block is unique up to an isomorphism, our object is isomorphic to the mode transition algebra as a V tensor 2 module. So this is our strategy. So there is nothing to do with the strongly identity condition.
Are there more questions? Okay, if not, let's thank Hao Zhang again and all people for today. Thank you.
Please remember that we start tomorrow at 9:45. There's will this presentation and welcome the Institute and welcome by the director.
So you're saying? Rational case, I am.
On the
non-rational case. And then they're using their proof uses.
I mean, in rational case, they of course they use the.
Yeah, so their proof is about using that.
Yes,
and,
yes.
And you guys
For rational
saying
case,
I can't go through that.
No.
I mean, even in principle, I can't go through that.
not in a logarithmic case.
I still have the results, but even though I can't pass through the nodal picture.
You mean our? Yeah. We do not
This
use
is
this.
like one way of thinking about it. Is like I can't pass through the boundary. Like essentially, I cannot pass.
What we actually do is like, well, I mean, the vector boundary, the spaces for classified in such a way, probably if you modify the definition of nodal conformal, it may still have a one, but it definitely is not like in this way. Define nodal conformal. By definition,
I think so. I think.
Yeah, because I guess like
I'm not sure if they are isomorphic to each other, but
you have some very
it
clear
must
idea
be.
which ones have a sphere, and you're saying that propagates.
yeah.
And then in the nodal case, I guess I don't have like a smooth
Because I
sphere.
think the information they have are the
You know, the right definition or something.
What is fusion course, right? So
Yeah.
this is
Oh, yeah.
Get vector.
Yeah, this is the one that's called down for
Wie das noch morgen, dass wir uns da
Yeah, if you have these two functors and for x and y here,
kann es wieder aufschreiben, was
Ja,
ich
kann
möchte.
dazu kommen.
and this is the fusion problem. Yeah. And Professor Gui has talked about this, but in my talk,
Yeah,
I
I wasn't
haven't.
here last week, unfortunately.
Yeah. But I haven't talked about this in my talk.
Yeah, because I think I remember reading this in your paper, but I wasn't sure about it.
Yeah. But I think you can check that they satisfy the same universal properties that they are isomorphic to each other. And I really don't have time to talk about our space of conformal block, the relationship between our space of conformal block and the Logarithmic modular functor. And it's like, maybe I can write something to you here. I'm not sure if you, our conclusion is that